All right. Good morning. So last time uh, we were uh, studying Banach contraction mapping theorem. What was a contraction mapping? It's a function on a metric space, so that for any xy, it satisfies this inequality. So there is some lambda, so that for each pair of points, the distance between the images of these points is less than lambda times the distance between the 2 points. Okay, so a contraction mapping is just sends points to points which are closer to each other uh, by the factor lambda, where lambda is a fixed number, positive number, or maybe 0, but it should be less than 1. Okay, and to prove this theorem, okay, the theorem was this: if you have any function like this, a contraction mapping, then there is a unique point, so that f fixes that point. In other words, f of x0 is equal to x0, and we call this point a fixed point of f, and this theorem tells us that a contraction mapping has exactly one fixed point. And for the uniqueness part of this theorem, we wrote this argument. So if you have two fixed points, let's say x and y, then the distance between them is equal to the distance between their images, because f of x is equal to fx x, and f of y is equal to y. But by definition, this is less than lambda times dxy, where lambda is less than 1, and it gives us this 1 minus lambda is positive, and dxy is a non-negative number, and the product is non-positive, implies that dxy has to be 0. In other words, x has to be equal to y. And for the existence, the argument is as follows: you start with any point and form this sequence. You just keep taking image of that point. You obtain a sequence, and we claim that that sequence is a Cauchy sequence. Since we assume our metric space is complete, this Cauchy sequence has a limit, and this limit turns out to be the fixed point of f. Why? Well, f of x0 is equal to this. Since f is continuous, well, why f is continuous? Any contraction mapping is continuous, right? You see, if you have a contraction mapping, you have this. Therefore, if you just, for any given lambda, if you choose your delta to be epsilon over lambda, then it shows that f is actually uniformly continuous. Not only continuous, but uniformly continuous, right? Maybe I should mark here, taking delta to be epsilon over lambda. We see that f is uniformly continuous. Okay, so f is continuous, therefore I have this, but f okay, the sequence xn is defined this way, so f of xn is equal to n xn plus 1, and the limit, of course, of this sequence is the same as the limit of xn, which is x0. So f of x0 becomes x0, so that x0 is a fixed point. So we will be done with the proof once we prove that this is a xn is a Cauchy sequence. Now let's see why xn is a Cauchy sequence. Okay, well, we will proceed as follows. Now for any, is there any question so far? For any n larger than or equal to 1, we have what? The distance between xn and xn plus 1 and xn is equal to what? Well, this is, of course, just d of fxn fxn minus 1. Maybe I should say greater than or equal to 2. And yeah, no, times lambda. I should write this. This is d of f of xn minus 1, and this is less than lambda times d xn minus 1. And then by induction, I just keep doing this. Each time I replace this by lambda times dx something minus 1. So each time I will pick up a lambda factor. So this will give us what? Lambda, and I have to stop at this point, right? 2 and 1, because I start my sequence by x1 and then x2 and so on. So I have to stop at this point. And what will be the power then? Each time I will pick up a lambda factor. So if you decrease this by 1, you get a lambda factor. So I guess, so the power of this plus this number is n. So it should be n minus 1, right? Sorry. So we have, okay, we have this, and then we proceed as follows. Now let m larger than or equal to n. Okay. Then we have what? Distance between dxm and xn. What is this? Well, this is of course less than dxm xm minus 1, dxm minus 1, xm minus 2, up to where? Up to here, okay, so up to xn here, and here I will have n plus 1. So I just keep decreasing the first index till n plus 1, and I stop here. So I just use triangle inequality several times. Okay, well, what is this? We just showed that here n plus 1 n is less than lambda to the power n minus 1 and then this distance. So here n is m minus 1, so we have lambda to the power n minus 1. N is m minus 1, so this is m minus 2 times dx2 x1. What about this? Well, this will be something similar, but with one less power of lambda as the factor. I have this up to this, which is the exactly this term. So n minus 1 dx2 x1. Okay. Now let's see what we have. I have this common term, so we have this x2 x1 is the common factor, and then I have lambda to the power m minus 2, lambda to the power m minus 3, and up to n minus 1. All right, this is the smallest power. Let me take it outside. So I have 1 plus lambda, and it will go up to lambda to the power m minus 2 minus this. So it is m minus n minus 1. Okay. Right, m minus 2 minus n minus 1 is this. And of course, we should keep in mind that lambda is something between 0 and less than 1, right? So this is larger, so less than the infinite sum, 1 plus lambda till infinity. So it is less than, let me write it this way, lambda to the power n, and from 0 to infinite. And this is just the geometric series, and we can just compute that thing. This is just 1 minus 1 over lambda. So I have this, okay, dx2 x1 lambda to the power n minus 1, 1 minus lambda. Here, this is true for all m n, right, larger than 1. Now, lambda is less than 1, therefore, and this is just a fixed number, right? Now, limit of lambda to the power n as n goes to infinity is 0, since lambda is less than 1 and positive. And therefore, and thus, so if epsilon is given, we can choose n0, so that lambda to the power n0, this thing is less than epsilon over 1 minus lambda times the distance between x2 x1. Of course, there is the possibility that this distance is 0, but if this is 0, if this is 0, if this is 0, this means x2 is equal to x1, but x2 is just f of x1. So I already obtained the fixed point, right? F of x1 is equal to x1. I would be finished. So we may assume that this is not 0, okay? So let's choose n0 like this, okay? Then if m and n are larger than n0, then the distance between dxm and xn, which is less than dx2 x1 lambda to the power n minus 1, 1 minus lambda, but n is larger than okay, maybe I should choose like this. Yeah. N is larger than n0, therefore this is less than dx2 x1 lambda to the power n0 minus 1, because the bigger the power, the smaller the number because lambda is less than 1. Okay, I have this, but you see this expression lambda to the power n minus 1 and 0 minus 1 times okay, yeah, I think I made mistake here. So I want this to be less than epsilon. So oh, okay, yeah, I should be more careful here. I should choose this epsilon times 1 minus lambda divided by dx2 x1. Yeah, okay. I choose my n0 like this. Now this number times this divided by 1 minus lambda is less than epsilon. So we are done, right? Yeah, hence xn is Cauchy. And this finishes the proof. All right. You see, if lambda is given, we choose n0 so that this happens. And if m and n are larger than n0, then this distance is less than epsilon. All right, so we proved the Banach contraction principle or Banach contraction theorem that any contraction mapping is a unique fixed point. Okay. Last time one of your friends asked me a question and said, can we relax the assumption that, you know, f x y, f of x, f of y, the distance between them is less than the distance between x and y times lambda by just ignoring lambda or taking lambda equals 1. I will give you an assumption, example, uh, uh, so that which shows that you cannot take lambda to be 1. Okay, the assumption that lambda is less than 1, okay, cannot be weakened to lambda equals 1. So I cannot allow this lambda equal to be 1. Here is a counter example. Okay, take x to be the metric space 2 to infinity with absolute value metric. Okay, so this is a complete metric space because real numbers with absolute value metric is complete, and this is a closed subset. Therefore, this is a complete metric space. Take this, which is complete, which is a complete metric space. And f to be this function from x to x by f of x equals x plus 1 over x. You see, if f of x was only x, then any point of x would be a fixed point, right? So this function is slightly bigger than x, so that it has no fixed points. Okay, clearly f has no fixed points. This is always larger than 1 because x is a positive number, so that f has no fixed points, right? It is never equal to x. Has no fixed points. However, it satisfies the following. We have for any xy in x, we have, let's see, what is this? F of x, the distance between f of x and f of y, dfx fy. Well, this is just x plus 1 over x minus f of y. I have this. And this is equal to what? This is x minus y plus the distance between them. This is y minus x times x minus y. And this can be written as x minus y, and then 1 minus, okay, let me write this, x minus y plus no, uh, uh, 1 minus 1 over xy, right? This is equal to this gadget. Yeah, because this is x minus y, this is y minus x, so I have minus sign here, and this is just x minus y times 1 minus this number. But you see, x and y are at least 2, therefore this number is at most 1 over 4, therefore this thing is less than uh, you know okay, so this thing is less than 1, sorry, less than 1, but if x and y are larger and larger, then 1 over xy is almost 0. Therefore, this number is less than 1, but for big x and y, this number will be very close to 1, because x times y will be very big, 1 over x times y will be very small. So I have this because this is less than 1, but I cannot put a lambda here because this number gets closer and closer to 1. Okay, so my f satisfies this. The distance between fx and fy is less than the distance between x and y for all xy, but I don't have a lambda factor here which is less than 1. I cannot put. And this function has no fixed point. Okay, therefore the assumption, the hypothesis in the definition of a contraction mapping, that you have a lambda here which is less than 1 is very important. You cannot just drop it. This function is something like this. It is so if this is, let's say, y equals x line, this function is a little bit larger than, right? So when it's 2, it is like this, 2 plus 1 over 2, but then it gets small, closer and closer to the graph of y equals x, right? Because it is just f of x is just x plus 1 over x. So it gets closer and closer to this red line, but it is never equal to that. Therefore, it has no fixed point. Okay, so okay. Is there any question so far? Okay. Ses az mı geliyor? Ee, Şimdi iyi mi? Tamam. Sanırım şey biraz açıkmış da şey kapalıymış sesi. Tamam. Peki. Sorusu olan var mı? Is there any questions so far? Okay. Let's see. Now we will make the next thing will be an application of this Banach contraction principle to differential equations actually. So we will use this result to prove the existence uniqueness theorem for ordinary differential equations. All right. Let me remind you what was the existence uniqueness theorem for ordinary differential equations, and then let's see how we can use this theorem to prove that. You have seen existence uniqueness theorem for the ordinary differential equations in the second year. But you didn't prove it because it was, kind of difficult back then. Existence uniqueness theorem for ordinary differential equations. Okay, what is the theorem? Öyle mi? Şimdi nasıl? İyi mi? Eğilince mi acaba? Ha, belki şey olmuş olabilir. Bir saniye. Acaba bir saniye. Yok. Şuradan değil de. Okay. Şimdi daha iyi değil mi? Tamam. Mikrofonu zoom bunu değil de bilgisayarınkini alıyormuş o yüzden. Tamam. Ee, Teorem şu. Consider the ordinary differential equation or maybe consider the initial value problem. So it is this one, fxy, and where f from R to R is a continuous function, is continuous uh, and del f del y. Maybe I should write and continues on some rectangle R, and this rectangle is given like this: x minus x0 less than a, y minus y0 less than b. Okay, so I have a rectangle around the point x0, y0, and on that rectangle both f and its derivative with respect to y are continuous. The conclusion is this: then there is a unique solution y equals phi x of the initial value problem defined on some interval x minus x0 less than epsilon. So maybe I should write it this way: for some maybe I should write not epsilon but delta, for some delta positive. So this theorem tells us what? Here is the xy plane, and here is, let's say, our rectangle. Okay, let's say this is our rectangle, and this is my point x0, y0. Okay, and this theorem tells us what? There is some delta, so that so this is the delta interval, and on this interval this equation has a unique solution. Okay, so this is y equals phi x, and this phi satisfies this differential equation that phi prime x is equal to f x phi x, and at x0 it takes the value 0. Okay, this is the theorem. Okay, how can we prove this? Well, as I said, we will use the Banach contraction principle. This is how we will do it. And we will prove this using the Banach contraction principle. Okay, here is what we will do. Okay, first we convert the initial value problem to an integral problem, integral equation problem. It's a differential equation, right? We convert this to an integral equation. How? Well, we will do this. Our equation is this, right? Y prime is equal to f of x y, and y x0 is equal to x0. This means actually y prime x is equal to f of x y x, right? For all x, I can just integrate both sides and obtain this. So uh, yx minus yx0, which is just the integral from x0 to x y prime t dt, right? This is the fundamental theorem of calculus. Integral of y prime from x0 to x is equal to this gadget. But what is y prime t? Y prime t is just f of, I just put t here, yt, and then dt, right? So I have this differential, integral equation then. So we have this yx is equal to yx0, which is just, sorry, this was y0, I'm sorry. Okay, plus x0 to x f of t yt dt. So, and this is y0. So this is the integral equation. Okay, integral equation. And what we see, if y is a solution of this differential equation, initial value problem, if it's a solution of this initial value problem, then it's a solution of this integral equation. And conversely, if y is a solution of this integral equation, then it will be a solution of the initial value problem. So conversely, if yx satisfies the above integral equation, then uh, taking derivative of both sides, we get what? We get here derivative of yx is just y prime x. Derivative of y0, this is a constant number, it is 0. And then derivative of this with respect to x. Here, this is the function of t. You differentiate with respect to x, you get what? You get f, whatever the function here, you take it and plug x for t. So you get x and then yx, right? This is the equation. So you get y prime is equal to fxy, and also moreover, if you plug x0, you get what? Y of x0 is just y0 plus x0 to x0, right? If I plug x0 here, then this integral becomes from x0 to x0. But if you have an integral from x0 to x0, of course, this thing is just 0. Therefore, you get y0. Uh, hence, yx solves the initial value problem, initial value problem. Which problem? This y prime is equal to fxy, right? Y prime is equal to fxy, and y of x0 is equal to y0. Y x0 is equal to y0. So what we see is then the integral equation is equivalent to the initial value problem. Hence, thus the I.V.P, let's call it star, is equivalent to the integral equation which integral equation? This one. Yx is equal to y0 plus x0 to x f of t yt dt. Okay, and from now on I'll just try to solve this integral equation, not the initial value problem. Okay, from now on let us concentrate on this integral equation. Okay, so we will try to solve this integral equation. How can we solve this? If you remember from differential equation course, there we explain how we prove this theorem, right? How we solve this equation. We use so-called Picard Iterates, right? Okay, so to solve this, we will do the following. To solve this integral equation, we use so-called Picard Iterates. What is Picard Iterate? It is the following. You start with a function, and then the idea is this. You have y here and y here, right? That's why this is a difficult equation. The function you are trying to find is contained inside f. So the idea is to take distinct elements. So differentiate, take two different y's. Replace one of these y's with another one. And we do it as follows. Start with any function y1x, okay, and let y2x to be this gadget. So I will write y1 here and y2 here, okay? So y2 is what? y0 plus x0 to x f of t y1 t. Then define y3 to be y0 plus the same thing, x0 to x f of t y2 t dt, and so on. And similarly yn plus 1 x to be y0 plus x0 to x f of t y1 t dt. Okay, so this way we obtain a sequence of functions y and x. Okay, I start with any function y1 and then I defined y2, then y3 and so on. Okay, I just keep putting that y inside f, take this integral, obtain a new function, and then just repeat it. Okay, we will see in the next hour that this sequence of functions converges to the unique solution of this integral equation. We will see that. We will use contraction mapping theorem, but we have to make a little. We have to be a little bit careful. I didn't tell you where are these functions are defined, right? I just said that they are just functions, but I should tell you where these functions are defined, and there I have to be careful so that I can also make use of Banach contraction principle. So I should have a contraction mapping constructed so that I can use it. Okay, I'll do it in the second hour, and along the way we need a concept called Lipschitz condition. Okay, let me do it in the second hour, this part. So let me stop here.